In this session, we will talk about total internal reflection. By Snell's law, we know that N1 sine theta 1 equals to N2 sine theta 2. So sine theta 2 can be re-expressed as N1 over N2 times sine theta 1. As N1 is larger than N2, if sine theta 1 is larger than N2 over N1, then by take this condition into the Snell's law, we will have sine theta 2 is larger than 1. And we know that for this situation, we cannot find out the real solution for theta 2. This means that we will have no reflection. For this situation, we call it total internal reflection, or just TIR. Okay? So, as theta 1 is larger than theta c, as the instant angle theta 1 is larger than theta c, which is defined as arc sine N2 over N1, then we will have this condition, we will have this situation, then we will have the total internal reflection. So theta c, which is defined in this way, we call it critical angle. This is what we have learned for total internal reflection before. And now we like to know that as the instant angle theta 1 is larger than critical angle theta c, we will have total internal angle. And at the same time, what will be the wave properties of the transmitted wave? Okay, and to find out the transmitted wave properties as TIR happen, then we will try to use this figure to explain that. And for this figure, we have a plane interface here as the x-axis. Above the x-axis is the material 1, and below x-axis is the material 2. The material index for material 1 is mu0 epsilon 1. For material 2 is mu0 epsilon 2. And in material 1, for all waves propagate to the interface, all the k vector can form the semicircle, the blue semicircle here. So this blue semicircle is represent all the k vector from material 1 to the interface here. In the same way, in material 2, all the k vector from the interface to the material 2 will form the red semicircle here. Okay? And due to we have said that epsilon 1 is larger than epsilon 2, which also means that index n1 is larger than index n2. So the radius of the blue semicircle is larger than the radius of the red semicircle. Okay? You may ask why they will form a semicircle here. As we know, for plane wave propagates in material 1, the k vector will have two components. We call it kx1 and kz1. Okay? The summation of these two components will equal to k1 squared. And the k1 is omega times square root of mu 0 epsilon 1. So all the k vector in the above region, they have the same value of k1, so they will form a semicircle here with the same radius. And all the k vector in material 2, they also have the same magnitude of k vector. We will have the square of ks2 plus the square of kz2 is k2 squared, where k2 is omega times square root of mu 0 epsilon 2. Okay? Or you can just say which is omega square mu 0 epsilon 2. And for k1, it is omega square mu 0 epsilon 1. So the radius of the blue semicircle is k1. The radius of the red semicircle is k2. And from this figure, we can easily to find out the transmitted wave, as we know the incident angle. For example, if we have an incident wave like this, then this one is the incident angle here, and this is the incident wave. And from this figure, we can find out the corresponding ks component here. Okay? This part is ks1. And for phase matching condition, we will have the tangential component of k vector should be continuous at the dielectric interface. So we will have the tangential component of k1 is kx1. The tangential component of k2 is ks2. They should be equal to each other. So we can denote them as kx. Okay? Since ks1 should be equal to ks2, so if we know the magnitude of ks1, then we can have the magnitude of ks2 here also. Okay? So this is ks2 and this ks1. As we have found out the magnitude of ks2, we can then obtain the corresponding transmitted wave under the theta 2 here. Okay? So this figure can help us to find out the transmitted wave from the incident wave. But now, let's consider the situation of total internal reflection. As the incident angle theta 1 is larger than critical angle theta c, then this situation can be plotted in here as, let me use the color in this one. As theta 1 is larger than theta c, it may look like this. The black arrow here represents the situation as c dot 1 equals to c dot c. And the brown arrow here is c dot 1 is larger than c dot c. And clearly, for this situation, you can see that the kx component, kx1, which should be equal to kx2, is larger than k2. Okay? Clearly, the kx component, kx1, is larger than the radius of the red semicircle. Due to this situation, we can say that because kx2 is larger than k2, but kx2 still have to satisfy that kx2 square plus kz2 square. The summation of these two should be k2 square. So, to satisfy both conditions here, we will have the conclusion that the kz2 square, the kz2 square should be smaller than 0, which means that the kz2 square is a negative value. Okay? So, we will say that the kz2 is an pure imaginary. Then we will take this into here. Then we will have kx2 square minus alpha z2 square is k2 square. So the kx2 larger than k2 makes sense. Okay? And as the TIR happens, we will have this conclusion. Then for TE wave, we take T wave for example. For T wave, as TIR happen in the region of material 1, that is Z is smaller than 0, the field expression are the same. But however, in material 2, that is Z is larger than 0, the EY field now is written as the amplitude of E plus 2 times exponential minus alpha Z2 Z times exponential minus JKXS. And the HY field is written as in this way. Okay, from the expression of the EH field in material 2, the transmitted region, we can see that along the x direction, you will see that the wave properties is exponential minus JK sub XX. Which is a propagating wave. But in Z direction, the wave properties is exponential minus alpha z2 z. Sorry, here I missed z here. And as we know, this kind of function represents the decay function. Okay, this means that as TIR happen in material 2, we will have wave propagating in x direction but decay in z direction. As a result, this wave will propagate along the surface because as it into the material 2, it will decay to 0. Such kind of wave, we call it surface wave. But commonly, we will call it evanescent wave. Okay, so this is the wave properties for transmitted wave. It will be a surface wave or evanescent wave, which will decay in z direction.